The father of PostGIS Day. Without your sand and the oyster, we would never have had this pearl.
Actually, let's clarify that because I don't want to take too much credit. I am the father of crunchy data PostGIS, virtual PostGIS day, and the
Yes.
sand and the oyster was COVID. Had it not been for COVID, this would still
True.
be an in-person event, traveling around, be the Stephen Paul show. Welcome to St.
Yeah.
Louis, and it's just Stephen Paul all day long.
Yeah.
So that's what it would have been had we not had COVID. So
Yeah. Oh
anyway,
well. Good
yeah.
things come from terrible things sometimes.
Exactly.
So
I
I
mean, it
was
was really
gonna,
great that first year because we got to basically all the
yeah.
time it was just you and I show, and now for once we were like, oh, I want to get Randy Hale, even though I'm in Santa Cruz. I can get Randy Hale to speak. Oh, I can get Brian Timmody to speak. Like we're not flying anybody anywhere. We got Ford that year. That was fun.
Yeah, yeah.
So anyway, I guess we should
All
get
right.
to the topic because the time is short and there's a lot to teach. So
Take it away.
okay.
Thousands of divisions.
All right, so let's start my slide. Well, let me start sharing my screen first. Share, and then this is not what I want. I want the entire screen. Share. Okay.
That's
And
working.
good. And now I'm going to start my slideshow, and
That's
we're
working.
good. All right, here we go, people. Strap on in. So, Brian called you friends over and again, again, again. I'm calling you campers, or I'm calling you rocket ship attendees because there's way more than 30 minutes of material that I have to cover actually to get to the interesting PG vector part working with PostGIS. So we're going to go fast. You're going to watch the recording later, and you're going to let this just kind of wash over you. And the reason why is because, well, that's the URL for the deck, but they'll have it as well. This is me. That's where I work now. It's computer vision stuff. And the agenda gets you to this, all the steps before you actually put your AI vectors into the database, because that's actually the hard part that most people don't understand and don't know. So we're going to go over that. Then we're going to show you it very quickly in Postgres. And then I might get into this, but the slides are there and they explain themselves. And then this actually just makes you the life of the party. I mean, the whole point of doing this is next time you go to a cocktail party, you start talking about, hey, I've put my embeddings in Postgres and then I mixed them with PostGIS and I use vectors from both of those. It was amazing. Yeah, people flock, life of the party. All right, so what is a vector database? The easy answer is it's a data store that works with vectors. And in this case, I want to make it clear we are not talking about geovectors. There's no geovectors up to this point, and there won't be for a while. These are what in the well, it's not really AI, it's just really, 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 really good machine learning, but they like to call themselves AI, and I like to humor them. So we'll say it's AI. These are AI vectors. They're also called embeddings. They're also called sometimes features or feature embeddings. That's what we're going to be working with today. But let's talk about what these things actually are. So the basic idea of the whole thing is with embeddings is you're turning things into numbers, right? This is basically going with unstructured data and then making it something a computer can understand. And so the idea behind this is hey, computer is 2 less than 3. It says beep, boop, 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 flip some bits. Great, 2 is less than 3. I can tell you that. I say, is this kitten picture less than this kitten picture? It says beep, boop, boop, boop. I have no idea what you're talking about. The only thing your computer can tell you natively about these two pictures is that are they equal? Is it the exact, I mean, exact down to the pixel and the band within the pixel exactness, or where are they different? Other than that, the computer has no idea what to do with all these pixels and the bands within the pixels. For this audience, I'm going to assume most people know remote sensing and that there's multiple bands in a picture and all that other fun stuff. I think that's a pretty good assumption with most of the people here, I think. Um, if not, you just found out. Pictures are pixels, and each pixel can have up to multiple bands. This is the same stuff that we do in remote sensing. All right, so we want to actually do something with this picture. Like we want to do something. We have all these cat pictures, kitten pictures, and who doesn't really? And so we want to be able to ask questions of the pictures. So the first thing we do is we bring neural networks in. And so it's neural networks to the rescue. So when we put all these models that everybody's talking about, these transformer models you might have heard, and then these other foundational models and all that other stuff, those are just neural networks is really what they are. And for those of you who if you really want to step back really far and think of what a neural network is, it's a really, 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 really fancy, good regression model. right? And it's a model, we can do models for two different reasons. One is understanding, like if I turn the temperature up by this much, how much does it expand? And that's our parameter in the regression equation. And then there's models where like, I don't care how you tell me, just tell me if that stock price is going to go up or down tomorrow. And that's a prediction model. And neural networks are prediction models. They don't really care about understanding the processes underneath. They're just going to help you make a really good prediction. And in a typical model, this is just a 2-layer neural network. In the typical models we're talking about now, this will be 5, 6, 10, 15, 20 layers deep, and with many more nodes than what I'm showing you here. So sometimes when you see these models talked about, you'll see like the Llama 3B. What that means is that's the Llama model, and it's got 3 billion parameters, and that's billion parameters. So if you remember your statistics, this is a lot of parameters you're going to fit, which is why these models are typically very data hungry, right? Because you're super fitting a bunch of parameters. But it's also why they do a really good job of predicting, because they have so much flexibility, all those parameters. Anyway, you feed your cat into the neural network, and then out of the neural network, it does a whole bunch of stuff inside. And then what comes out of it is an array or a vector of numbers that are supposed to represent the semantic meaning of the picture. What do I mean by semantic meaning? It captures the je ne sais quoi, the essence of the picture, right? So for like text, it captures the essence of the text. I don't know a better way to explain it, but basically what, like in images with neural networks, what it does is at the first layer, we just break it up into pixels. And then in the next layer, what's happening is it's starting to look for features in the image, like lines or edges or contrast changes. And then as it moves through different layers in the network, it starts putting those features together to make other features. So like, oh, that when the lines are like this and it's kind of dark and the rest is light, that's usually a nose. Okay, and a cat usually has pointy ears and a nose. And so by the end, that's what you're getting to. And at the last layer, you're basically breaking it into all the classes you want in a classification model. All right. And then what comes out is a vector, an array of numbers, right? And because computers can work with numbers. This is typical sizes for this vector is 512, 256, 1050, I don't know, all those multiples that we do for our RAM and our disks and all that stuff. So that's typically the size they use for the vectors. That vector size stays the same per model, and it's always going to fill in the entire vector. This is considered a dense vector, if you hear about it. This is the point at which I would ask everybody, do you understand? But since I can't see anybody, I assume you will. Paul, if there's a question that I can answer that helps clear that up, let me know. So basically, again, one last time, because this is the essence of the whole thing. You put the unstructured data, whether it's a full book, right? You take your whole book and you figure out ways to get that through and into the neural network, and out comes vectors of numbers. Same thing with an image, same thing with an audio file, any of this unstructured text, which the computer doesn't really know what to do with. And what comes out at the end is a vector representation of that input in a way that has captured the meaning of it that's related to what you want. All right. And I'm going to keep going at this point because we don't have much time. You're like, Steve, you're going so fast. How can we not? Because there's a lot to cover. So even though this is PostGIS day, some of you will probably do what's called NLP, which is natural language processing, because you might have captions or you might have descriptions that go along with your geographic entities, and you want to use similarity search for that. So there's two important things in NLP. This is like OpenAI is actually doing this behind the scenes when you send it text. When you send text to OpenAI, it's doing these two things, which are chunking and tokens, right? So chunking, you can't fit the whole book into that model, right? It can only take so much text, so many tokens. And so what you do is you have to chunk your book. So chunking is how you break up the thing you're trying to put in into things that can fit in, but still retain some sort of resemblance or key idea. So for an example, my friend and I were he was trying to get OpenAI to be a dungeon master for Dungeons and Dragons, and it was doing a really bad job because it kept losing context, like idea of, it can't hold all that stuff. Like this is what a cobalt is, and this is, because it's just trained on general text. So a solution to this is something called retrieval augmented generation. And with that, you use similarity search to give more information to the search so it remembers things. Well, so in this case, we found all the 5th edition manuals for Dungeons and Dragons in Markdown format. And the chunking strategy I used was Markdown headers. So every time you came to a new Markdown header, that would denote a new chunk of text. So if there was a single hash, then there was some text, 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 text. Then there was a double hash. Everything between the single hash and the double hash, that's one chunk of text. And then starting at that double hash, it would start, that's another chunk of text. So in that way, I could break up the Dungeon Master's Guide into relevant chunks that I could feed in one at a time or parallel into the model itself. Okay, so that's a chunk. Now, that's great. You've got a chunk, but now what do you do with that chunk? Like, how does a computer understand what those characters mean? So that's where tokenizing comes in. And if you've used Postgres free full text search, you tokenize as well there. Basically, what tokenizing is changing the string of characters into things that you want to keep as a representation, right? And so, for example, well, no, not for example. I'll show you an example in a second. So when you tokenize something, that thing then gets that token then gets a number, and then you do counts and all sorts of fun things against that number whenever that chunk of no, I shouldn't say chunk, bad word. Whenever that token appears in your text or your image, right? So that's tokenizing, and I'll show you. It matters because this is what OpenAI charges you by, right? Chunking has a huge effect. So if you're going to do any NLP stuff with any moderately sized text, you really need to pay attention to chunking. Because it actually ends up having a huge effect on how well the similarity search does. The other thing is chunking is related to what's called context length. You'll see this discussed a lot. What's the context length of that model? And everybody likes to brag about a big context length. Context length is how big of a chunk can you fit in at once, right? And so that's what that matters as well. And then the other thing is tokens matter because that's what OpenAI charges you on, right? So for example, OpenAI has a little thing so you can play around with some text and see how that works. So we'll pretend we're using one of the fancy new models, ChatGPT 4.0, and we're going to say PostGIS Day 2025 is the best event ever for PostgreSQL, right? And then I can say, okay, this is my chunk, tokenize it for me. Oh, nope, that's not what I wanted to do. Will it put it back? Nope. PostGIS Day 2020. It's because the text is too big here. If I scroll down, there you go. PostGIS 2025. Oops, wrong year. 2024 is the best PostgreSQL event ever. So naively, we would say, look, tokenize it. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 tokens. No. So what you see down here below, let me zoom it back in again. Each one of these different colors is a token. So it is tokenized PostGIS into Post and then GIS. Those are 2 tokens. 2024, it says 202 is a token and 4 is a token, right? And so what PostgreSQL, that's also 2 tokens. So usually the advice is you get about 30% more tokens than the text, the number of words you put in. The other thing is you need to pick your tokenizer carefully. This tokenizer right here, it's going to have a little bit of a harder time dealing with dates, right? Because it's actually split the token into being 202 and 4. So you pay attention to your tokenizer when you're thinking about your problem set. And what is it splitting? You may be able to give it rules about what to split. You can in the in Postgres full text search. All right, but we're not really text people for the most part. I just want you to understand this because everybody's playing with OpenAI and blah 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 blah. So let's keep going. Any questions yet, Paul? Or am I going too fast for people even to type them out?
Go.
Sorry, keep going. All right, keep going. All right, so now we've gone ahead and we've made that vector, and this is an embedding. Right? And so there are more and more embedding models to use. Like, how do I know which embedding model to use, right? And there's a lot of them that come out all the time. And so I can't tell you exactly which one to use. I'll tell you some of the things you should think about and then what I've been doing, right? So the ones that we care about today for this talk are what are called, they're pre-trained on large data sets, and they're called like foundational models, right? So Clay or Earth Genome Project, if you've been doing any of the remote sensing data, those are foundational models. They went out and trained their model, their big model, on a lot of information. And so it's really general, like any of the OpenAI or Claude models, it's really general. It was crawled on the entire internet. And they can just give you the weights, although OpenAI does not, nor does Claude, but they can give you the weights and then you can just use that model as is. You don't actually have to train it. The only drawback is it's a bit general. There's ways to deal with that, but we can't go into that today. But those are the ones you mostly are going to be dealing with, for them, at least in the beginning. There are several things to consider when picking a model. One is the appropriateness for task. So almost every one of these models is built for a specific task. like even within images, like remote sensing, right? We do object detection and we do segmentation. Object detection is show me all the trees in this remote sensed image. Segmentation is take this remote sensing scene and make it into a complete tile of polygons for each of the different data types. Right? Those are two different models, and the models, I mean, those are two different tasks, and models can work differently on each one. So it might be good for object detection, but not as great for segmentation. When I would try to pick based on appropriate for net task, because everybody says theirs is the best for everything. The way I usually do it is there's usually some leaderboards that are out there where people compete on Hugging Face for who's got the best model to do the best text model, embedding model, and they compare it against a bunch of different benchmarks. And some of those benchmarks are more appropriate for other tasks than others. So you'll see some of the models do well on some of the benchmarks, but terrible on the others, while the next model will do terrible on the ones the first one did, but did really well on the others that it didn't do well on. So you would pick the second one if that was like the task that you were doing. In general, though, you're pretty good with any of the more recent models, especially when you're just getting started, right? Like you don't even know what you're doing. So just pick a model and see how it works. When you really get to it, so there's this interesting curve. Like when you really get to it, you've gone through the, oh, I looked at Hugging Face and what's like, which is one's the best for my task. And then you pick like 3 that are best for your task and you run them all and you actually compare it to the thing you're actually trying to do. Because there's nothing that replaces how does it do on your actual use case. Right? All right, size of input, this is that context length or image size that you can put in. Depends on how much, all sorts of factors go into that. The length of the output vector, the bigger the vector, the more information it can hold, right? So the more meaning it can grab from the original thing that it had. In general, that the bigger the vector, the longer it takes to calculate and the more space it takes up, right? So it's this and the next couple things I'm going to talk about, it's always a trade-off between accuracy and speed/cost, right? Because speed usually translates to cost. You can make things faster by usually throwing a lot of money at it. So it's accuracy versus speed. Right? You might pick a very, very accurate model if you're doing some offline batch process that is not time sensitive. But then if you're building a model that has to run on a phone, it's going to probably be pretty small and less accurate because you need it to work in real time on the phone. So just depends on your use case. So that's what I was saying here too. And I'm not going to show this today because we don't have time. But Hugging Face is the GitHub. Well, I'll show it quickly because I can't withhold stuff, can't keep secrets. This is the GitHub for the machine learning community. Okay, so they have models, which is what we're talking about now. They also have data sets if you want to play with them. NASA and IBM has a remote sensing foundational model in here. I think it's called the PIFI, I forget the rest, IBM AIMS something. But you can see, remember I was talking about all those different tasks. So like here within computer vision, here's all the different types of tasks you can do and whether that model will work for that. If you're going to start getting into this stuff, this is your GitHub, your new GitHub. Right? You're going to be coming here and looking at stuff and looking at what people are talking about and discussions on the models. One thing to know is there's official and unofficial repos just like GitHub as well, right? So here's OpenAI Whisper Large 3 V3 Turbo. So the fact that this is from the OpenAI org means this is, and it's got that nice pretty picture, means that this is from that organization and it's their model. If you look at something like, let's see, I saw one yesterday. No, these all look pretty formal. Let's just go ahead and click on depth estimation. And then we'll look at like this one, Lee Young, depth anything small HF. This is some individual who's taken one of those foundational models, trained it or done something different with it, and then trained it from scratch, not even a foundational model, just a model architecture and trained it, and then putting it up on Hugging Face. And you can play with it, but it's just like downloading somebody else's code as well, right? You don't know, no one's certifying it. You don't know if it works, how well it works, any of that stuff. So this is Hugging Face. You need to get get familiar with it. All right, back. Even though we don't have time to show it, I knew I had to, so let's go back. Okay, great. Now I have all these embeddings. I ran all these embeddings against all my cats. What do I do with this? Well, it turns out what those embeddings are actually coordinates. Right, so suppose our neural network actually only gave out a 2-length vector. It's actually giving us the X and Y coordinates. And if the model is good at the thing that you want it to do, when you go to plot those coordinates, or whenever you compare against those coordinates, things that are similar, or the things that you want to be similar, should be closer together in the space, like the kittens, and things which are dissimilar should be farther away. So what that is what this is the semantic meaning we're trying to get at and why it can depend on the task and you have to play with it is basically you're taking this cat and turning it into a set of coordinates in some high multidimensional space. So if it's a 512 length vector, that's a 512 dimensional coordinate space for cat pictures, if that makes sense. It's not 2D. My brain can get to about 3D. I can't even think about well, I can almost get to 4, like when you move a block through space or something. But like past that, no. And so I can't visualize 512 dimensions in space, but 2 dimensions is just the same process and you just keep moving out, right? And this is also why accuracy improves, right? I don't know if you've seen this, but like in classification algorithms, you have to actually look at my picture of me on the screen now. Like sometimes you'll look at a picture and you'll say, how much do these things overlap? And in 2 dimensions, they overlap completely. But if you turn to the third dimension, if you add a third dimension, which gives it the Z, there's actually 0 overlap, right? And so the more dimensions you add, the more ability for the computer to actually take things and break them into discrete groups or find ways, distances, like how close is it really, and all these things. Does that make sense? The precision on that vector can differ as well. It can go all the way from like down to bit, like 1, 0. Some people do binary quantization, is what it's called, all the way up to B binary 32-bit floating point, I think. Sometimes 64, but I don't see anybody ever really using that. Okay, so but back to this, what we're doing is we're making an unstructured thing into a coordinate space so that then we can do mathematical operations with it, just like we do in Geo, right? And now this is because you're Geo people, I get to ask this question and nobody gets to answer except for maybe either Paul or Elizabeth because they hold the mic. But we've been doing this embedding. This is why they call it embedding, right? You take the picture and you embed it in a coordinate space. I don't know why they had to come up with that name, but whatever. We've been doing this embedding in Geo way before they were. We have taken unstructured text and turned it into a 2-dimensional embedding for a long time. Actually, Regina is going to know the answer to this one, and that's a hint to everybody else about what it is. Regina mentioned it earlier today. Paul?
Geocoding.
Exactly. Geocoding is an embedding process. We take a unstructured text, which is an address, and we turn it into 2 coordinates. So that's the exact same thing that we're doing here, except on a way more sophisticated and with a lot more different things and more general case. Okay? So that's what you're doing. So now we're into vector space. You're like, great, now I've got I went through and put all my kittens, I'd made all the embeddings, I put them into a database, that's great. I did my dogs, I did my horses, I did all these things, they're in a database, now what can I do? So what you're gonna do is you're gonna wanna make a query, right? That's usually what we use databases for. You don't use embedded, well, you can use embeddings to do summaries, but it's a different way to do it. You're not really doing any direct operations on the embeddings. What you're usually doing is a similarity search. So questions of what is similar to this thing or what is close to this thing. So the question we're gonna ask is what picture is similar to this picture? So we're gonna get this picture that comes in, another great little kitten, right? And we give this to the database and we say, hey, here's the 2-dimensional embedding that we embed it. We say, what's close, what's similar to this 2-dimensional vector of this kitten? So what picture is similar to this kitten picture? And if our model has done a good job of embedding, I have to move you guys because you're up there. The green dot is our new kitten, and these are our 2 kittens before, and this is our dog, right? And so what should happen is we should say, oh, well, these are the things that are similar to the things that you asked for, right? And so what it's going to give you back is a ranked list usually based on distance actually. And you don't, as Paul is often to point out, do not store the image in the database. Just store a reference to the image, but you'll have it'll come back with rank order and then a reference to the image that you care about. And it's by default, it's usually no, I put it wrong. It's usually in increasing distance order, right? So closest is at the beginning and it gets bigger as it goes down. You can sort in reverse order and it will give you the thing the most dissimilar, like an anomaly, some sort of anomaly or something. But that's what comes back. The other thing is, because this is not some sort of exact query, right? We're just saying, hey, what's similar? It will theoretically go through and calculate distances between your new kitten and every other embedding in that database. So usually the extension or the database has some default number that it returns, that it won't exceed. But usually you'll do something like, say, I want the top 10 or the top 20 or the top 40, but you're not going to ask for the entire database to come back. Okay, good. How are we doing on time, Paul?
You got 5 minutes.
Fart. Okay, I'm not going to discuss the index. It's really cool. I want to show you the demo, right? So this is the demo of how that all comes together. I'm using GitHub Codespaces, right? And so this is, let me just go to this one more time so you can see there's a link in the deck for this. You'll go to this code space in my GitHub repo. You say code. Usually you're looking at local. You click on code spaces. You'll say code spaces. You say new with options. Just because we need a little bit more memory, you'll say I want a 4-core machine. And then it spins up this, which is like a VS Code editor with a bunch of containers running in the background so that I can do things like it's already got Postgres set up with my one of my Postgres images that has PostGIS and PG Vector already in it. PG Vector is the extension we're going to use today. What we're using is the Google Landmark data set. This is from a Kaggle competition. Google's original competition was, hey, here's an image. What landmark is this image of? Right? So they have like, I forget, several million images of landmarks, and you're supposed to be able to train a model so that if I give you an image, it tells you what it is. I was like, but there's no geo in that. This is boring. So what I did is I took one of their Parquet files, so like 100,000 images, and they give you the Wikimedia URL, and some of those URLs, some of those pages had coordinates, so I scraped the coordinates off those pages and associated with the image. And then I went about it. They already gave, and then I calculated the embeddings for each of those images and then put that into a Postgres table. So I'll show you quickly. Here is how you, let's see, this is how we make an embedding, right? Thing Vision is one of the Python libraries. Sorry if you don't really know Python, but it's the language that most people work in this space, and so you have to at least be able to read it. So we're going to say, hey, we're using the Thing Vision library. If there's a CUDA, like an NVIDIA GPU available, then use it. Otherwise, use the CPU. The model type, the model name is called clip. This is a very common image model. The variant of it is this variant. So I'm defining my model. I'm going to get an extractor. So an extractor is what extracts the embeddings. So I give it the model, the source, the device. I basically copied and paste directly out of the text in Hugging Face. I say, here's where the images are, the number of images to submit at once, and then here's where the data set is. And then I say, okay, data loader, load up that data. And then I say extractor dot extract features from that image I put in, or any of the images I put in, right? And so it goes through and generates the embeddings. And you can pass in multiple at a time, but for me, I'm just getting the first one, and I'm actually then putting it I'm returning that from this function. So that's all it takes. Almost everything that this is copy and paste. This is actually all it takes to make embeddings. It's actually quite simple to make them once you understand what the libraries are doing, whether it's a good embedding or not. It's kind of like, using SAS or any of those statistical software. I can do a regression, no problem. It's just, did you shoot yourself in the foot? So you really just need to know your model name, which variant you want to use, point it at your data set and say, hey, give me some embeddings. And it's as simple as that. All right, so then this is, let me see what's in this one. Okay, so this one is, I'm going to show you now the Psycho PG stuff from the Postgres stuff, right? So if the database already exists, drop it. Otherwise, create the database, connect again. This is the extension. The new one to people on this call, on this webinar, is Vector. That's PG Vector. So we add that extension to our database, and then we connect again, and we drop the table from that database if it already exists, just because I keep running this. And here's the important part for the input of the data. Everything else here should look totally normal to you, right? It's a geography, it's a point. I'm going to have a column named embedding. It's of type vector, and this %s is a substitution in Python, and it's saying this is the size of that vector. You cannot change the size of that column. This is not one of those ones where, oh, it was 212 text. Well, now I want to make it 512 text, right? Like you can't do that. Once the embedding size for that column is set, you can't change that embedding size. But that's all it is. It's just a very simple column call. And so then here we're just pushing it all in, not a big deal. And then this is making the index on the spatial. No big deal on that one. This is that special index I couldn't talk about. By default, most Postgres ships with 4 megabytes of working memory. There's no way you're going to create one of those indexes in that much memory. So we set the working memory higher. I'm creating the index. Here's the name on this column using, and this is the HNSW, hierarchical navigable small world. The column that I want to do it on is embedding. And with all of these distance metrics, you have to pick a distance metrics to use with all these distance calculations. You can use Malin-Hoba distance, you can use geometric distance, you can use Manhattan distance, all these other ones. The one I see most people use is a vector cosine distance, right? And so that's what we're saying. When you go ahead and make the index, when you're calculating the distance between all these points, use cosine distance operator, and that's the distance that will get used in our queries as well. This one just says how dense is the network. It tunes the specificity of the network. So that, and then you're done. Bob's your uncle. Again, caveat, this is the expensive part, the memory intensive part, and every time you insert new entries, it's going to recalculate that index. So try to batch that up when you insert new stuff so you're not constantly running that index creation. All right, so here's how we do the query. So this is the image. My idea for the app was I like going to forests and going hiking. So when I go to a country to go speak, I want to see places that I want to go to places that look like this. This is where I want to go. Show me places in that country that look like the kind of place I want to go to. All right, so the query, and I didn't talk about this before, I forgot to, and it's a really important part. When we make the query, the embedding that we use, the model that we use to embed has to be the exact same model that was used for all the other embeddings. And you should understand this from like doing projections, right? For going from a globe to a 2D space, right? You can't mix and match different projections. Well, those models are making a coordinate system. You can't mix and match coordinate systems. So you have to use the exact same models with the exact same parameters on both sides. All right, so again, nothing new has happened here. This is all exciting. I would just return an embedding, right? Exactly the same. The interesting part is what we do with the database, right? So what we do with the database is, this is the big part you have to learn, but this should actually look familiar. It's also a I think it's a PostGIS operator, or maybe even just a generic Postgres operator. I'm sure Paul can correct me on this one, but it's near what's closest. It's a distance operator, right? So basically what I'm saying in this is select ID, and then select the distance between my embedding column and the query vector I sent in, call it distance, the file name, the URL column from images, order by the distance, limit 10. Right? You could also, if you wanted to, you could say, you could order, or you could do a where clause and say where embedding distance is less than a certain distance, if you had a better preconceived notion about what distances are valuable. So that's it. So to run this in Postgres, it's like simple. You make the embedding. As long as you know how to do that, you basically make an embedding column, make the index, and then insert, and then query the data using SQL with just one new operator, and that's it. If you do not make the index, this will do the distance calculations between all the points and the vector you put in, which is not fun. So, but if you have made the index, this is smart enough to know, hey, there's an index, I'm going to use it. All right. But that's just a vector query. Where the geo one, and this is why I love Postgres so much, because now I get to combine all that fun embedding stuff with everything else Postgres does. So nothing about this, now that you've seen that query, should look new at all. This one I was like, okay, I got a table full of world ISO codes with their polygon boundaries. And so I say, here's that distance operator, greater than, select these fields. Images is the I table, world is the W table, which is where I have the outlines. Select where the 2-letter code I pass in equals the ISO code, and of those with the ISO code, where their outline intersects the point of the image. And
1
then
minute.
I order by, sorry?
Blow our minds. 1 minute to blow our minds.
Okay, here it goes. Ready?
Yeah.
Let me make sure I didn't do any I have to change here. There's one thing I do where I like to show how you do the inverse. Yeah. See, that would have been the inverse. It's easy to do the inverse. Here it comes. Boom. So we're going to get to, it has to load the model, and then, it actually may have to load the model. While it's doing that, in case it takes more than 45 seconds, oh, no, it's done. All right, so it's done. This is what it says if I just do a generic one. Right? Somewhere in Germany, I think that is, right? But it's a forest. Ta-da! I mean, that's pretty nice. Like, I don't know how else you would have gotten that without this kind of query, like that this is actually a forest, unless someone labeled it. Now I was said I wanted to do it actually in Canada. So here's what it looks like if I say I just want it in Canada, because who doesn't love Canada? And that's what it looks like now. You can see it's somewhere in French-speaking Quebec, and it's a forest again. So this is the part you can, all that other stuff you can do with PostGIS, all that other SQL, you can match it to all this other similarity search and do all sorts of really incredible things. Quick thing that I want to show that I just showed before. I know you gave me a minute, but I'm going to take a minute and 30. Because we're using the cosine spatial operator and because of vector geometries, I can just multiply this by -1. Oops, I did it the wrong way. -1, and I will get the least, where's the star? I will get the least similar image to my image. So this is the thing I don't want to go to. Ready? And this is the least similar image to my image. Ta-da! Right? And I don't know how else you would do that without like these embeddings and similarity search. So it adds a whole new level of capability to what you can do with PostGIS and spatial stuff. And this is what people are doing when they talk about all this fun new AI stuff. It's a big part of it. The slide deck, the rest, it's just here's good things to know, why they're good, what kind of use cases to use them for. Isn't this great? Hang on. Here's the slide URL again. And then if you want to read more about retrieval augmented generation, there's a little bit here.
Say
Ta-da!
goodnight, Gracie.
Sorry.
Say goodnight, Gracie.
Wait. Say it again.
Say goodnight, Gracie.
Oh, say goodnight, Gracie. Good night, Gracie.